So we'll look at this problem, 35. We may or may not follow the steps as recommended. I'll just tell you how I would work this type of problem. So we're supposed to find the focal length of a mirror that produces a given magnification. So we have a magnification of 1.5, and the person's face is 12 centimeters away. In other words, our object distance is 12 centimeters away. And so the first thing we can do is say, well, the magnification is given by minus the image distance over the object distance. And so since we have the magnification and the object distance, we can find the image distance. So if we do this, the image distance, if I just solve this equation, is equal to minus the magnification times the object distance. And so putting those numbers in, I have the image distance is minus 1.5 times 12 centimeters. I don't have to change to meters as long as I keep this because magnification is unitless. And so that gives me a value of negative 18 centimeters. What does the negative sign mean? Well, it means it's a virtual image, which shouldn't be a surprise because I have a positive magnification. It's an upright image. And in fact, if you have a makeup mirror, you certainly want your object to be upright. You don't want it to be flipped upside down because that would make it very difficult to be useful. So an upright image is also going to be a virtual image if you're using just one mirror. So if we then take this, we've got our image and we've got our object distance, then we can use our other equation, which says 1 over the object distance plus 1 over the image distance equals 1 over the focal length, and that will get us the focal length. So 1 over the object distance is 1 over 12, we're in centimeters here, plus 1 over a negative 18 centimeters. You can't get rid of that sign just because it's there and it feels inconvenient, otherwise you'll get the wrong focal length. So when I plug this in, you want to make sure that you invert both of these numbers, and when you get finished, you invert again. You get, for your focal length, you get a positive 36 centimeters. And it should make sense that it's a positive number because, of course, 1 over 18 is a smaller value than 1 over 12. So we are going to be left with a positive number. So I have a focal length of 36. Now to check this answer and to see if it makes sense, I'm actually going to draw a ray diagram for this setup because that's a good way to check. So we're saying that it's a focal length of 36, a plus 36. If we had a minus, then it would be a negative mirror, but this is a positive mirror. Okay, so let's try again. There's the mirror. And we're going to say our focal length is here, so that would be 36 centimeters, but we've put the object at 12 centimeters, so about a third of the way in, right? So that's our object distance at 12 centimeters. And so when we do this, we can draw our rays. The rays I like to draw are the ones that come in parallel and then go out through, ooh, that's not very good, go out through the focal length. Okay, so that's one of the rays that comes from the top. And then we can take another ray which would go from the top to that central point and then bounce off at equal angles. And the thing to notice is that if somebody's looking at it back here, I realize the eye is probably actually where the object is, right? But if you're looking at it, if you're capturing these images, these rays, they converge behind the mirror, right? And so this convergence behind the mirror is where we see our image. So our image is going to be right here. This is our image. It is bigger, so that's as expected, 1.5 times bigger. I probably drew it about 2 times bigger. This is not quite 18 centimeters behind. Probably it's a little more, so it's just exaggerated a little bit. But this is consistent. So this is a way we can check and have some confidence in our values. Our focal length seems good, and this shows us the diagram of what's going on. So in fact, we have a focal length of 36 centimeters. We have a concave mirror, and we have an upright and virtual image. And again, it's virtual because the light rays are actually not back there. You can still see it. It's an image that you can see. It's just not one that if I put a piece of paper right back here, I wouldn't actually capture any light rays, right? Because it's blocked by the mirror. The place I would pick up light rays would be over here and over here, but that would not be a focused image. We can see a similar type setup, but this time with a convex mirror, where we're given sort of the same information. We're given a shopper is some distance from the mirror and sees an image, again, magnification. So this is going to set up pretty much the same way. So magnification is -1 of image over object. Again, it's an upright, so we've got a positive magnification. A negative magnification would mean you'd see yourself upside down. So you have a 0.25 or 1/4 equals minus image over object, which is 3/4. So your image distance is -3 meters times 0.25 is -3/4 of a meter. Okay, so that's your image distance. So that's the question. Where is the image? It's 3/4 of a meter behind the mirror. And then the focal length of the mirror, we're going to do the same thing we did before. 1 over object plus 1 over image is equal to 1 over the focal length. This time we're working in meters, so 1 over the object is 3 meters plus 1 over 3, a -3/4 meters equals 1 over the focal length, so this is 1 over 3. My focal length is going to be in meters, minus 4 over 3 is equal to 1 over the focal length. So I have 1/3 minus 4/3 is equal to 1 over the focal length, and so that gives me 3 over 3 or -1 meter for my focal length. And so if we set up the sketch of this, we would have a convex mirror. We would set up the person here, say at 3 meters away, and we would say there's my focal length about 1/3 of the way through. And to check this, so that would be my focal length, the negative focal length be behind the mirror. So I would say if I have light that comes in parallel, it's as if it comes off of the focal length. The thing to notice about this kind of a mirror is it's a diverging mirror. So the rays that come in are going to go away from the optical axis. That is this central line that I have here. So that's diverging out. And then I'm going to draw in a second ray going towards the middle and then coming back out. And so that would be my second ray. And again, for somebody looking at it, where these rays come together is behind the mirror, right about there. And that looks like okay. The image is about 1/4 of the size, right? Maybe it's closer to 1/3. And we're about 3/4 of the way there. So that's what we expect as that this is, in fact, consistent with what we had worked at.